point load, but I've crossed this fourth one. If you see, like if you can imagine why, is because it is in the pier zone. Okay, so it will not be a part of the cantilever moment that is supposed to govern the design load case for designing the pier cap. Okay, so we have these point loads which are directly incident upon the bearings. So we have a force which is actually acting upon them, and with this subsequent lever arm, okay, if you see lever arm, we'll have different lever arms. So the lever arm is taken with the reference point of the pier face. Yes, pier face. And this is the lever arm. If you see over here, this is the lever arm for the point load, which is P3. This is P2, and this is P1. Okay, so you can say this is lever arm number 3, this extending up to lever arm 2, and this one lever arm 1. So the moment which this load P1 is generating upon the pier cap is M1, which is P1 into LA1. Okay, similarly P2 into LA2 and P3 into LA3. Since this is in the pier zone, this load will not be considered in transverse moment. Okay. Similarly, for the right hand side, both of these will be considered with maybe LA5, LA6, and this is going to generate a moment. So now the moment from this is the transverse moment from the left hand side and the transverse moment from the right hand side. They're together going to nullify each other, or we will have to calculate the net moment. Like for example, if this is 100 and this is 50, so the net moment is going to be 50. Okay. Similarly, you'll have to design the pier cap for that. So this is only the force. You can say it's sort of a force diagram, but since this is a cantilever pier cap, the extents of these are too long. So for that, we'll need to be designing it as a post-tension pier cap. So this is same pier cap. This is the stress arrangement, cable arrangement. If you see, what this typically is that these are the cables for post-tensioning. These are the anchorages. I've just indicated them this way. These are the distances from the top. And you can say if I've taken a section from over here, or if I see this pier cap from over here, I'll look into this diagram. Okay. So talking about the profile first. So this is the cable profile. All right. So if you see over here, we'll have rather straight profile, and over here we'll have a parabolic curve. Okay. So this is basically done in order to take care of the moment that is going to be generated. That is why the eccentricity at the center point is more. Over here it is less. Okay. This would be the combined CG of the strands, all the strands. We've got many strands. Like for example, if you look at this diagram, we've got about 10 strands with an addition of 2. So what this typically means is the stages of stressing. Okay, when we are stressing any structural member, it has to be done in stages. Okay, why we use these kind of construction stages? I'll discuss this when we are actually dealing with some detailed design. Okay, and we have to also give a provision for future pre-stressing, just in case we happen to encounter a problem that the beam is not being, the cantilever pier cap is not being able to accommodate that much load. So in that way, we'll have to leave two cables for future pre-stressing. Okay. So as you said, these 1, 2, 3, 4, these have been done in stage 2. 1, 2, 3, 4 have been stressed in stage 1, and stage 3 has only 2 stressing cables. Okay. So this has to be exactly replicated in the software that you're using. Basically, what we used was Midas Civil, and we had to try we have to try a very rational approach, and we had to experiment a lot upon what should be stressed first, what should be stressed later. Moving further, these are portal piers. We've encountered these a lot, and basically when we use it is that when the distance between piers, when it is not feasible for us to have a direct pier over here. Okay, as you see over here, there's a different bridge. So we have a limitation that we cannot have a direct pier over here. So hence we'll have a portal frame. Okay, so this typically is a frame like this, and the girder would be over here. And we can have different variations. Okay, like for example, this is pier 1 and this is pier 2. You can have a variation like this. Pier 1 is deeper, pier 2 is much lighter. Maybe the rock is like this, or something like that. Okay, we can have pile foundations for this pier. We can have open foundation for this one, as well as combination of girders. Like for example, over here we can have box girder. Over here we can have I section girders. We can have more than one box girder. So it typically is based upon the layout and what is your requirement. So these are, this is a sketch briefly indicating what are the different components of portal pier. Okay, if you see over here, these are different sections. What is the section of the portal beam? If you cut it over here, you'll get a section like this. It's like a T-beam. This is a cobble section. Cobble section is this one, this zone, which is actually hosting the piering and the seismic arrestor, and subsequently the superstructure, the box girder and the pier section. Okay. If you see closely, this is the cable profile. Okay. The cable profile has to, as I said, has to be modified and has to match the requirements of the moment that is generated. Okay. Yeah, now coming to station piers, this is one of the most interesting elements of elevated metros. Why? Because the challenge exceeds a certain limit in this, because usually station piers are supposed to have an aesthetic appeal. So an architectural consideration has to be also made. Okay. So any station that you might have traveled, you might have seen that it is comprised of many different piers. So one station is supported by multiple number of piers. So maybe this entire station is supported by 8 number of station piers. When we designed Mumbai Metro, it was one station was supported on 10 different station piers. And second of all, I'll also show you how many levels are there to a station pier. Okay, and if you see over here, this is rather a huge shed. Okay, so for this, a separate arrangement has to be made. It should be supported. The load has to be supported sufficiently supported, and so the number of challenges that we face in designing station piers that goes well beyond a certain limit. Okay, so this is a general elevation for a station pier. It is rather it looks like quite a hodgepodge, but if you see, it is it is more about levels and dimensions rather than components. So if you see over here, they've indicated number of levels. What is the level of this? What is the level of that? Similarly over here, there are some levels mentioned over here. Okay, later on there are some dimensions mentioned. So typically this is your station pier. Okay, this is your station pier. I'll show you the next slide. This is a station pier. Okay, these over here, what you see are the concourse arms. All right, these are cantilever arms which are stretching out from the pier. This is the pier. This is the pier cap. If you see over here, this just has got one level. Over here, we've got number 1, number 2. Okay, there's also one more level over here. So now, having seen this photo, it is easy for you to understand this pier in the context of the architectural drawing. Okay, so now this is your main pier. This being the first arm. Okay, these are the I sections which are supporting the deck over here. This is where the pedestrians are. So these are the stairs. These are the stairs that you take in order to get to the metro bogie. This is the metro bogie. All right. This is the first arm. You can say concourse arm. Over here, the pier is extending. This is a pier cap. The box girder. And finally, over here is a separate arm, which is a platform arm. So this is typically the platform. So this platform arm is supporting the I section, which is supporting the deck, which is supporting the pedestrian. So the pedestrian is going to the metro from over here. Okay. And as I said, this all these architectural elements have to be supported. There are huge loads. These generate huge loads, especially wind loads. Okay, so these are station piers as constructed. So this is a typical segmental launching. So these, you can see segments are being joined and lifted one by one. This segment already casted, and this is the staging arrangement. So this is concourse arm 1. This is, I believe, this is a platform arm. Okay, over here, if you see, this is entirely post-tensioned. Okay, since we are talking about huge moments, it is imperative that we go for post-tensioned. Okay, so this is typically a sketch to throw some more light. All right. These are station piers with only 2 levels. This is level 1, level 2. We can have station pier with 1 more level. I'll show you that in the next slide. So basically, the station pier can be broken down into 3 main parts: the main pier, the pier above the concourse arm, and the pier above the pier cap. Okay, so this is the main pier. This is the pier above concourse arm. And there's a simple pier over here, which has to be, which sockets this platform arm. This is called as pier above the pier cap. Okay. So I've tried to simplify this as by medium of the sketch. So this is typically a 3-level station pier. Okay. So with pile foundation, this is the pile cap. Do I have a, no, I don't. Okay. So over here we have got a pile cap with piles and a crash barrier, crash parapet. And so this is your main pier. This is the pier above the concourse arm number 1. This is pier above the concourse arm number 2. And this is pier above the pier cap. So why I'm typically showing you this is that you need to understand the number of girders that are actually incident upon the concourse arms. So if you see, this is basically a pier like this. Okay. This is a pier. All right. And the section is decreasing. Okay, that is for obvious reasons, because the axial force is increasing. Okay, so these arms are stretching out from the pier. So these are actually cantilever arms. Cantilever arms. Okay, they're trying to deflect like this. All of them. Okay, so having said this, I'll clear this off. Okay, so if you saw the first drawing, this one, you can observe over here that yes, all of these I sections are going to put on, they're going to put loads upon the bearings. Okay, these I sections are placed upon bearings. All of these I sections will be placed upon bearings. Okay, so whatever the moment and the loads, they are directly going to be transferred on the concourse arm by the bearing. Okay, so these are the bearings. So now you've got point loads all on the bearings. Okay, so as we had seen in the case of cantilever pier cap, the lever arms, different lever arms, similarly will have different lever arms generating a higher magnitude of moment. Okay, the moment the lever arm will start from the face of the pier. Okay, so we'll have different lever arms, like for example, we can say this P1, 2, P3, and P4. Similarly, we'll have lever arm 4, we have 3, 2, and 1. So all of these point loads, they'll generate a moment. Okay, similarly, they will generate a moment. This is level 1. On level 2, a similar case would follow. We'll have moments. We'll have moments. This would be an increasing magnitude, or it might also decrease. The lever arm is not only the concern. Why? Of course, because if the lever arm is more, you'll have more movement. But it is possible that the moment over here, maybe this is 100, and it is possible that this would be 50. Why? Because it is not only a matter of lever arm, but over here, maybe if we have some furniture or if we have got a machine like this, okay, the SIDL load is more. So the point load itself is maybe 1000. Okay, and the lever arm is less, so we'll have a higher moment, and we don't have any loads over here. So the dead load and the live load will not be sufficiently creating a higher moment. So it is highly possible that the moment from this is less than this, regardless of the fact being that the lever arm is less. Similarly, on the platform arm, we'll have a similar case. So this is what makes it so complicated. All right. As also we have a, as you saw, we have a box cutter over here. So this will also have loads, okay, as well as moments. If the bearing is not in the pier zone, then it will generate a moment also. So all these moments have, as I said, you'll have to subtract the left and the right moments, and you'll get the net moment. So we'll have to represent all the net moment, whatever is at this point. Okay, and similarly, you'll have to design this pier. Sorry. Design all these piers separately with the moment that they have, as also the actual force that they have. Okay, so I've resolved this into a sketch. If you see over here, this is a pier elevation. As you see, this is an axial force diagram. So on the pier cap bottom, okay, over here, this is the axial force. As you're going down, the axial force is increasing, and for the main pier, the axial force is small. So the main pier will be designed for this. The pier above the concourse arm will be designed for this axial force, and the pier above the pier cap will be designed for this axial force. As also, it can be for earthquake design purpose, it can be resolved into a lumped mass. Okay. So this is the design, you can say, principle of pier caps, regardless of them being quite complicated, but they're quite interesting. Okay. So having said this, if you see the number of components that actually define a pier, a station pier, there are too many. So all of them have to be designed separately. So this entire pier, this has to be a separate design entity. This is one design entity. This is second design entity, the pier cap. The platform arm is a separate design entity. The concourse arm is a separate design entity. The second concourse arm is a separate design entity. So the crash barrier, of course, is a separate design entity. The pile cap and the foundation is a separate design entity. All the bearing pedestals are a separate design entity. It is possible that we'll just design one and we'll apply this for the most critical case, and we'll apply the same design for all of them. The bearing, of course, is a separate entity. The seismic arrestor is a separate entity. So you can see that there are too many design components that actually go into creating the actual submission for a design for a station pier. Okay. All right. So over here, the concourse arm. Okay. The concourse arm. This is a model that we had made for one of the stations. So as I told